right.
So well, I guess this is a bit of review though. We already did. Oh no, this is the one thing I didn't record last time too. It was the potential energy stuff. That's the only one thing I didn't record. So yeah, we set our zero value here. That means now the ball has negative 60 joules, giving you the suggestion that it needs 60 joules in order to get out of its it being stuck in the whatever the field, the potential energy well that it's in. Just again, like you guys would see, the first electron, or the electron in a hydrogen atom, right, has an energy state of negative 13.6 eV. That means it needs 13.6 electron volts in order to get out of its the electron's attraction to the proton. That's how much energy you need to give it in order to ionize the electron. Yes?
Yeah.
We're all right so far? So if I have more than that, it'll have some kinetic energy at the end. And we're going to see this again with like the photoelectric effect and all that stuff. But if it's not enough, it's going to basically go to potential to kinetic to potential to kinetic, potential to kinetic, or be stuck in an orbit or something like that. Questions, comments, concerns so far? All right. So, I'm sorry. That brings me then to, so we got this, well, let's see. So if I got the Earth, so, and then I got some object that goes from here, so there's its initial position, to here, that's its final position. So we're going to measure everything from the center of the Earth. So the initial position is here, our initial. Final position is here, our final. And I want you to find out what is the change in gravitational potential energy. And I'll give you a hint. You want to use the gravitational force equation. So let's see, is there anything else I wanted to go? Yes. So I'm moving my object from here to there. So initial position to some final position. And yeah, find out what the gravitational potential energy is.
I'm sorry.
So go ahead and try that.
Zach, I'm sorry. Zach, I'm sorry.
Probably guess it.
I had to sacrifice one building for 9. I got you. Mass of the Earth. Mass of object. Right? We're talking, right? Our initial square.
Oh yeah, then
Our new active.
I think you're doing it harder.
G and Earth object on R2 square, guys. Boom.
That's so funny. How do we get T? How do we get time?
Time. We don't need time.
See, yeah, you do need time.
Wait, is there another marker? We're changing G.
Let's show this one.
The change in gravitational potential energy. That's torque.
Or R.
Congratulations.
What's the R on the and MG is.
Here, guys want markers? I got markers over here.
No, I took the SAT.
No, you took Spanish 4 too.
Yeah, I know. But he took the test.
Oh, you took the test? You passed? Oh.
Where did it go from there?
Oh my god.
Oh, no, that's okay. That's all right. Keep working.
All right, so
Yeah.
G. All right, so G.
Yeah, I know. Like, some of them didn't take the train to SAT. There's no, like, they need to take
H's, RF, minus RF.
the test. That's all.
What's the energy?
Yeah, it's like a writing. It's read an essay.
No, that's...
Huh?
That's what I thought.
No, yeah, so by this, that was 7:30.
From the...
I'm like counting.
No, David,
Between
in
M1 and
Korean,
Well, yeah, sure. I can give you the math.
David, even for Korean SAT, you have to get 7:30 or above to get sealed, right?
Yeah.
7:30?
Wait, 7:30? Isn't it like kind of higher?
Well, so, I mean,
I thought it was 7:30.
gravitational
Wait,
field.
why? What's it get? Oh,
Oh, okay.
you're probably not getting it then. No, it's really competitive. Only like fluent Korean speakers take it.
Cycle something up.
No, I mean,
I know what it is.
Oh no, he said only fluent Korean speakers.
yeah.
He's way better than me at Korean. I got 800, you got 790.
Okay, the listening was kind of messed up.
wait, why did you get silver?
Guys, how do you calculate How do you calculate a potential function?
MGA.
MG change. Oh my god, it's not
What happens to the gravitational field from here to as you go to
It
that?
changes.
It changes. How does it change? Does it increase or decrease? It's gonna get weaker, right, as you go up. So this is now far enough distances that it's not uniform anymore.
Oh yeah.
So I gotta go back to, okay, how do I calculate any potential energy function?
That's a good.
Oh, it's
That's okay.
It's the negative integral
That's where we
of the force dr.
I would not guess that. You were on the track.
Guess that, you learned it.
I was doing this.
Wait,
But I thought I had
Wait, when did we learn that?
Last semester, during energy?
MGH, and I just fucking not for that.
Nope, that's not right. Sorry.
Alright, that's terrible.
So that's G over G.
Wait, I can take this.
We manipulate. Or do it. Distance is far, far away.
Wait,
What's the DR?
yes, but what about this is the dot product of those two things.
Are we integrating
From R1 to R2. Yeah. Yes. It's the work done. Work done is the dot product. It's the integral of the dot product of the force.
Oh my god, I'm forgetting how to do dot product.
Yeah. You should have. It was part of your homework. How do you integrate R squared in the denominator? So you take R and throw it in the numerator. R squared.
R negative.
Yeah, then you can integrate that.
That's 48.
That's so fun.
I don't think
Yeah, I know. I thought about it. Yeah, I know. It's a good chance.
We have
R to the negative 3. Integral, not derivative.
yeah, that's what
So what is this negative? No negative. And then the only other thing is this is well not DTDR. And then this is a dot product.
I'm sick.
30.
Same issue. This is cancel this. Oh yeah. And then this is a dot product between these two.
I think they just get a list of people for
And then evaluate from but I think you're having the same issue. This is the dot product between these two things. So what's the dot product?
I don't think it's a dot product.
This is funny.
It's gonna show my arm.
Oh, wait.
I like how I can just take it.
R
I
I minus
like
R
that.
divided by
That'd be pretty chill.
R I times R.
They don't cancel out. Well, they do cancel out, but then this is the dot product between two.
Big number.
I'm just gonna say.
Oh no, he's just another right. You see numbers now.
So guys, some more review.
Yeah, we get dot product. Woo!
A dot product between two vectors is the same thing as the magnitude of those two vectors
Times the cosine of this.
times the cosine of the angle between them.
Wow. I didn't know that.
So, which way is the force pointing here?
Cosine.
Down.
Oh, wait, so
Negative.
And which way is the displacement pointing?
Down. Oh wait. Oh, I thought it was free.
Yes.
Oh, so it goes back to negative.
You know, I'm gonna write that down.
And then forget about it again in a week?
Yeah.
Yeah, true.
Oh, thank you.
It's locked in.
It's locked in.
Is there sense?
See, I know that equation. I just didn't know that that's what that product was.
Wait, Mr. Forney, open your class for Saturday Academy.
I'm not this time, no. Sorry. I got a school thing that I was doing.
Yeah, Saturday.
What are the parties?
House table.
600? Bro, you get like 500 for writing your name.
Parties, no.
Wait, did we?
No, you need 600 to pass.
Oh,
You see, like, let's see.
Wait, do your teachers know that you're like a science teacher?
why is the standard so low?
Okay.
Yes, but then that's not how you would plug them in. You want to evaluate them between those 2 points.
So you have to take 4 years.
This is not the same thing as
Yeah, it's easy
this
though.
minus
Easy
this.
Wait, it's just another negative.
But I think pretty in 1 hour.
Alright.
Yeah. All these kids, I'm like, ay Dios mío. That's all I
Dude, last year Spanish was so fun.
It was a B.
Wait. We all try memorizing at the last moment, every skit.
Dude, our first dance. So like,
It was about watching us.
like, she literally just hated our class.
Yeah, there's like another step it's like where it's like 3 days.
So that's the negative integral of big G M1 M2 divided by R squared. So I'm gonna pull out, what's the variable here?
R.
R. So I'm going to pull out all the constants. So this is negative G, M1, M2, cosine of what's the angle?
180.
180. And what is cosine of 180? Negative 1. So this negative is going to cancel out with that negative.
I like the circle going.
And then I got the integral of 1 over r squared dr. From the initial position to the final position. All right? So this is now big G, M1, M2. And then this would be the integral. R to the negative 2 dr. What's the integral of r to the negative 2?
Negative 1 over.
Negative 1.
So this is going to be, r to the negative 1, and then a negative in front of there. So again, you add 1 to the power, and then you multiply it by whatever whatever result you get. So, or multiply by the inverse of the result. The inverse of 1 is just 1. So, okay, and then this is going to be evaluated from r initial to r final. So this then gives you Ug equals, I'll take the negative and just throw it over there. So negative G M1 M2 divided by R, evaluated from R initial to R final, which lastly is going to give me negative G M1 M2 divided by R, and then R final, so 1 over R, I'm sorry, not divided by R. So 1 divided by R final, and then plugging in R initial, that's going to be minus 1 over R initial. And that is the potential energy function between 2 points. So, and that's what people were missing, was this, which is important. Yes. Sure.
Wait, you keep this? You just leave the cosine until the end.
Sure.
So that's actually.
No.
Yes.
Oh, wait, no.
The same thing.
I need to let me look at it. I need to think about it, but just know how to do the integral. Because again, that MGH is an approximation, assuming the G is constant.
That's why we need to take the integral.
Yes. And especially because here's what happens is physicists go one step further. They go, if I want to, those of you in AP1 remember something like this, right? If I wanted to calculate the potential energy of this system, right? If I had 3 planets that are sitting here and I said, what's the energy stored in this system? I don't want to be able to go like, oh, what's the initial position of this? What's the final? What's the initial final of all this? I just want to be able to look at it and be able to calculate the potential energy of that whole system. So what we tend to do, and this is a way that we can kind of bypass all that stuff, is we say, well, I'll say my initial position, let's say, so let's see. Basically, we say, or how did I state it? How did I state it last time? Establishing our 0 mark. That's right. So we can establish our 0 mark wherever we'd like. And physicists say, well, I'm going to set my 0 mark at R initial equals infinity.
Wow. Whoa. Just make it a 0.
And then 0 becomes infinity.
Well, not in physics. We just go, oh, all right, so that's 1 over infinity.
Wow.
Really?
Limits?
Mr. Montrella?
What else? What else?
I'll legal that.
As I said in the last class, you also got upset when I did this. I went 1 over infinity. Yeah, that's pretty much 0.
1 over alright.
But yeah, what I said in the previous class too is, you know, mathematicians also told Newton that you can't, you know, you need 2 points in order to define a line. And he said, oh yeah, watch me. Calculus, yo.
How
How do you do that? How do you do that?
Let's go.
Yeah, that's what calculus is.
You make calculus.
That's what calculus is. It's
Oh,
defining.
yes.
It's defining of the slope of a line in just at just 1 point.
Oh.
Yeah, like the,
Yeah, tangent.
yeah.
Wait, what?
That's the difference.
Technically, Mr. Montrella doesn't do math.
Yeah.
I'm a top.
So again, yes, I know it's mathematically bad, but you know, it's.
Yeah, I do legal math.
Dang, Newton.
So yeah, so this goes to 0, and it leaves you with. It leaves you with. Gravitational potential energy is negative G M1 M2 divided by R. And huh?
Wait, why can we say that?
That's like
F?
that's
Our initial R is
that
R.
and like tiny.
Oh, we're just R. And so if you have some, if you've got 2 objects, so let's just say I had 2 objects, and those are their positions R away from each other. Their potential energy is that equation.
So we go from like
Yeah.
So,
square to 2x.
I don't understand the
calculus
starting
is
from
R.
infinity point. Like, that just doesn't
We go
like
from
add up in my
2x.
brain.
Okay. So yes, and exactly. This is where you're gonna have to sit and just not deal with it. Sit and digest it, because this is a tough concept to wrap your head around. It's huh? Well, not 1 over infinity. No, that and you're saying that setting the 0 mark in infinity. Why do it? Is that what you're saying? Yeah.
This isn't really
All right.
now, and I'm so behind. I'm doing
And one of the things you're going to see is what we're going to do soon is calculating escape velocities on different planets, and this makes it much more convenient.
Yeah.
That's one of the first things. But so
There's like some functions that you can't.
if I'm let's take everything and we're going to tilt it like this. So let me hold on. Let me
define it as a series. So I think it's like.
so once again, this R is like if I had, let's just say I had 2 objects. So M1 and M2, and then they're R away from each other. To calculate their potential energy, I would just need that. So, but it'd be negative potential energy. It'd be negative potential energy. Now, why make that the 0 point? And this may be helpful. It may just make it worse. But let's say here is the Earth, right?
Yeah.
And we're in the Earth's gravitational well.
Yeah.
And then there's the edge of the universe. Now, that's not exactly, you can get out of Earth's gravitational well without going to the edge of the universe, but we're just using the edge of the universe as a defining point. This is 0, right? This is 0, and that means everything below it is going to be negative, right? So the more negative you are, the less potential energy you have. I know.
That's a trip.
And this is the difference between a scalar and a vector. A scalar can be negative.
It just doesn't care.
It just means it's below the 0 mark. That's all a negative scalar means. Here is an example of a negative scalar. Which one is colder, negative 60 or negative 100 degrees Celsius? Negative 100. Yes, negative 100 degrees Celsius, right? So the more and more negative you get, the lower the temperature is. Why? Because we just set the marker there, based on convenience, And it's the same idea here. We set the 0 marker here based on convenience for some calculations we're going to do. Again, one of them is escape velocity, but also calculating potential energies of systems and things like that. So here's the lowest negative you can possibly have here, right? You're on the surface of the Earth. I mean, I guess we could dig into the Earth and be even lower, but yeah. So, and then as I do this, am I increasing potential energy or decreasing? Increase. So again, more potential energy, 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 until I'm at the maximum potential energy I can have, which is 0. Because if I let go, it's going to fall back. Right? And it turns out that that total energy that it has is finite.
Wow. It's exploding.
Yeah.
But isn't the universe infinite though?
What's that?
Isn't the universe infinite though?
It is infinite, but okay, I bring this to as far away as I could go.
That's why we round to 0.
It's, yeah, and we go, well, that basically goes to, and then that's where I guess I should have done the limit. Yeah, that's basically 0, right? So, okay, so that's our, yeah. And yeah.
But I don't understand how it gives us the potential, like, because if we're going like all the way here to the edge of the universe, like how does it give us the potential energy of the object right here? Right here.
So because we've set a marker as 0 over there, anywhere we go in the universe now, the marker for 0 is the edge of the universe for everybody. And that puts them all on a level playing field, and now we can compare potential energies between systems and things like that.
Oh, so it just makes everything like internal in one system.
Yeah.
Okay.
All right. Okay. So with the remaining time, we're going to calculate an escape velocity. Because just like, and you guys have less time, so I'll try and give you guys more of a hint. So, right, there would be a minimum velocity, v escape, that you would need in order to get this out of the well.
60 joules. So 1/2 empty square. 60.
So here you are, you're on Earth,
We just need some new ones.
and you want to send your rocket out of Earth's orbit. You want to get out of Earth's gravitational well, right? So what minimum velocity or escape velocity would you need in order to do that?
What do we use to put 5,000?
So again, the Earth has a radius r. And so, just like with this situation, to escape this we'll call it a gravitational well. To escape this gravitational well, how much energy do you need? 60 joules. So, oops, wrong one. So it's the same idea here. In order to escape, we don't know what this is. Let's say we don't know what this is. So, but if this was our rocket ship down here, right? Well, and this is my initial point, and we want our rocket ship to be up here, and basically have a speed of what? We're talking about the minimum.
0.
0. So velocity
squared would be 0.
final equals 0. So then, so if this is my final moment, this is my initial moment, what kind of energies do I have at the final moment?
None. Oh.
Yes!
You have none.
None! Gravitational potential energy would be 0.
Kinetic would be 0.
And the kinetic, it's not moving, so it'd be 0. But what kind of energy do I have at the bottom?
Gravitational
Gravitational potential energy
So kinetic
and
has to
kinetic
equal,
energy.
kinetic has to equal gravitational potential.
There's E escape.
The opposite
That's
way.
laser kick.
So,
Energy is
using the conservation
So
of
if you have
energy,
like -60, then you have to have -60 equals And you have to have 60 G.
I've got UG initial plus
Then it has to cancel out.
kinetic energy final, kinetic energy initial equals UG final plus K final, which yes is 0.
I was thinking like, how about we use it as our final point, but like, it's not our final point. We
So
have to
I've
do
got-
everything in the initial.
1/2 M V escape squared, and then I got big G
This does.
M1 M2 divided by R, but something's missing.
Negative.
Then negative in front of there equals 0. We'll say
Just the way I
massive
thought about it.
Earth,
I was tripping balls.
massive.
Now that is
So calculate that escape velocity.
So,
They're both the same thing. They mean the same thing. It's just MGH is for if the gravitational field is constant. If it's not constant, that equation just falls apart.